Well, welcome back once again, and now we're coming to the last phase of this course because now we're only talking about applications of all these things we have shown to you, trying to not only give you an idea of what are all those things good for, but also of um, how all these concepts we have been developing through this course they relate to what we can do with radiation. So the first thing to say is okay. Uh, every time we talk, I don't know the each person has a story on this. Once I decided to work with physics and specifically with nuclear physics, I had to hear at home, and my family is well scholared. So imagine when you go to places where people do not have the education my family has. And the first thing they said was, "Well, what are you doing? Will you be building nuclear bombs? You'll be radioactive, right? You will be glowing in the dark and things like that." So I guess one of the important things of these courses to show you that no, this is not true. There's much more than nuclear bombs, and there's much more than radiation, and radiation is not exactly what people think it is. So without further, let's go on. So when we talk about radiation and nuclear energy, the first, usually for at least for my uh, generation and the ones that came before me, first thing people think is fear. They have fear because radiation is bad for you, and nuclear is bad for you, and you have the atomic bomb, and it gives you cancer. Okay, all these things are true, but they're not all of what we do, and they are far from being the most important thing on what we do. And this down here is the symbol denoting the presence of radiation. It can be in pink, it can be in black, and it can be in red, and it means somewhat different things. But I hope you all know this symbol. It it means be careful. It doesn't mean be afraid, right? This is an important thing because fear is the father of most bad decisions we make, right? So one possibly the most important thing I have to say here is the difference between irradiation and contamination. Irradiation is when you expose something to radiation. Meaning, for instance, we have here me and here a source, and then radiation coming from this source will hit me, right? And so I'm exposed to radiation. But if I remove, I don't have to touch the source to be exposed, right? Because as we saw, radiation travels through the air and everything, and I can't keep this in my hand. Okay. Okay, that's essentially what irradiation is radiation from some source hitting my body. And if I remove this source, of course, there's no irradiation anymore. If I shield this source, there's no irradiation anymore. That's the great difference to contamination. Contamination is when, for some reason, you incorporate radioactive material in your body, or you may have an object is irradiated, is contaminated because it has incorporated radioactive material. Now we cannot. It generates radiation, right? Let's say my hand. I put my hand on a surface that was dirty with some radioactive material, and now I have radioactive material in my hand. I cannot shield it. It's in my hand. I cannot. The only way I can get, and now I'm being irradiated by it the whole time. The only way I can stop being irradiated is by removing this, which means, depending on the case, just scrubbing it until it's all gone, right? And yes, that's what we do, scrub and scrub a lot. But once I have removed it, okay, it's no longer radioactive. right? It can also happen when you inhale something and everything. So contamination does generate irradiation, but irradiation do not contaminate. Unless, of course, as we have seen, you're talking about neutrons, because then things may become radioactive. But on most cases, we only have that many neutrons in the reactor here, so that's where we have to be more careful. Otherwise, irradiation does not contaminate, but contamination irradiates, right? That's a very important concept here. Now let's go for applications, right? So this is essentially what we'll talk about, but let's go. First of all, I think everybody has heard of it, that we have nuclear physics is a source of electrical power. In Brazil, we have 2 power plants operating, 2 nuclear power plants specifically for energy production. We have a third one that's in development, has been in development for a really long time. And there's a long political debate whether or not to construct it, to finish building it, because everyone thinks of electrical power, nuclear power, they think Chernobyl, they think Fukushima. But those are very isolated cases if you think it's 2 cases in the history. In fact, there are 3. There's one way back in 3 Mile Island in the United States, but there was no person injured in that one. Just the facility that was completely condemned, right? So how does, when we say nuclear power plants, nuclear power reactors, we're always talking about nuclear fission power reactors. That's an important thing. We're talking nuclear fission. For the future, we talk nuclear fusion, but it's not available as of today. And what is a nuclear power plant in essence? In essence, a nuclear power plant is a thermoelectrical power plant. Just like coal-based thermoelectrical power plants, or oil-based or gas-based. The difference is, maybe we could say, our coal here is a bit more technological. Joking. The fact is, uranium releases much more energy per kilogram than, and when I say much more, remember that 100,000 times factor I told you in the first class. Yeah, it's 100,000 times more energy released per gram of fuel. So if we need 1 kilogram of uranium, we need 100 tons of coal. It's not exact numbers, but very, very close to something that could be true. So what is a nuclear power plant essentially? So here we have a pressure vessel, and this is a typical PWR reactor, pressurized water reactor. There are other models, much less common. This is by far the most common one. There's some changes between one and the other, and the most recent developments tend to take you towards some nuclear reactors that may not need that much pressure, and they deal with things in a different way. But I'll talk about pressurized water reactors. In the reactors part of this course, which is another module, they'll talk about the newer trends and everything. So what we have here essentially is the core is where uranium is where the fission happens and everything. It's made of some form of uranium, could be silicate, could be oxide. It's usually inside some kind of protective material, in cladding. In our case, it's can be stainless steel, can be zircaloy, which is a mixture of is an alloy of zirconium of some kind, thus zircaloy, right? And okay, it's in some form. and it's inside water. And this water is in a pressure vessel, meaning it will get to, if I'm not mistaken, 300 atmospheres or something, right? So it can get to almost 300 degrees centigrade also, without boiling. And this is controlled by some control rods, which contain neutron absorbing material, so that when fission starts to happen, these rods, you insert them a bit if you want to reduce your reactivity, and you take them out a bit if you want to increase reactivity, right? So here is where nuclear fission happens. Here is where neutron absorption happens. These control rods have to be made of neutron absorbing material. Usually they use a mixture of silver and cadmium and indium, but there are other options too. So that's essentially where the nuclear part of the things happen, because then you have the hot water coming down here and boiling another, and here it heats up a secondary system. There's a reason for that. You may think, okay, here we have all the nuclear things happening, we have a lot of neutrons, and neutrons make things radioactive. Even if this water is very, very, very pure, you will have minor things here that will become radioactive. This water has to be treated as radioactive. So once you do this, you may lose a bit of efficiency, thermal efficiency. But this second water here has never been close to nuclear fission or to neutrons. So it can be treated as non-radioactive, and then it can go outside the building, and you can do all maintenance on this part without fearing radiation, right? So we have a primary cooling system and a secondary cooling system. In most cases, a tertiary cooling system, but this one is only to cool the water of this. After it passes the turbine, you want to cool it down so it can enter cooler here and things go on. Okay, this is essentially what a nuclear reactor is. And if you ever curious about those big chimneys in nuclear reactors, it's essentially only water vapor, right? It's from the tertiary system. It boils water here, and then it just boils water, and hot water leaves producing a lot of water vapor, right? That's essentially, and that's why also sometimes we use to make the things close to the sea or to rivers or lakes, because this water here usually comes from the cool water, the cooler water, this stuff comes from the river, the sea, or whatever, right? So this is a nuclear power plant, very simple. You have nuclear fission. You remember it's you can have how is it called, a chain reaction, and when you insert the neutron absorbing material, you reduce the chain reaction because you absorb more neutrons. When you take these control rods out, you increase the chain reaction because you remove less neutrons, right? Okay, but then you may have heard, most people have, some people haven't, about nuclear fusion reactors, which they call artificial sun sometimes, because the sun produces energy just by this method, okay? So some people call it artificial sun. It's very good for headlines, not really true, but okay, whatever. And so what are fusion reactors and why are they so hard to produce, right? Because we've been hearing about them for a long, long time, and at some points we have the feeling that we are no closer to them than we were 30 years ago. That's not true, really. But increment has been very, very incremental, very small steps. The idea, okay, it's the best. You remember the three reactions I told you, right? Deuterium producing tritium, and deuterium producing helium. This one is the one that gives you much more energy. The other one is good for producing tritium, because tritium is not that common. It would be too expensive to get, and if you got all tritium in the world and put here, it wouldn't be enough. So we have to find ways to produce tritium during the operation, that reaction is one of them and releases some energy, by the way. One of the advantages, although we produce neutrons, we produce much less neutrons than before, because here is one neutron at a time. More than that, you don't produce fission fragments, so you may produce activation products, meaning this neutron, it can make nuclear reactions with things and make these things radioactive. But you do not have fission products, which are the main source for contamination and radioactive waste. So you have very little radioactive waste, and you may require neutron shielding because of these neutrons and everything. But the main problem here, these reactions requires that we have a deuteron and a triton. Both are charged particles. They have to be close enough for fusion to happen, and that means you have to overcome the repulsion, the electromagnetic repulsion between them. This means you need to have these things. They must have some kinetic energy, not so little kinetic energy. Well, we could do that by having some kind of accelerator throwing these things one into another, but efficiency would be very low. It wouldn't be enough for mass production of energy. It has been done, but you wouldn't do something that feeds itself and goes like the fission reactor does, right? So in this case, the way to do that is remembering that neutrons, they tend to be in thermal equilibrium with matter, right? So we have to do here what the sun does. And how does the sun get these neutrons to do these reactions? It has very, very high temperature. And remember, high temperature means very high kinetic energy for the neutrons. Remember, thermal neutrons, they are in thermal equilibrium, and the average energy is 3/2 of the Boltzmann constant times the temperature. So if I increase the temperature a lot, I increase the energy a lot. And so the problem is, we need this to happen, we need 100 million degrees Celsius. That's a lot, and very, very a lot. We don't know any material that would be solid at this temperature. So how do we do this? In the sun, that's no problem, because the sun is essentially a bubble of gas, right? Or in fact, we call it plasma. Just in case you don't know, we call plasma, what we call plasma, think you have a solid, and then if atoms are not so tightly bound, it becomes a liquid. And if they're not bound at all to another, we call it a gas. And now say the positive particles and the negative particles are all separated from each other, meaning there are no electrons in any atom. You have the nuclei and the electrons are all free. That's plasma. At this temperature, 100 million degrees Celsius, and it's what happens in the core of the sun too. The temperature is so high that the electrons, all electrons have energy enough to get free from their orbits, and so you have essentially a soup of nuclei, positively charged nuclei, and a soup of electrons. No electron has a real atom to be bound to, because they can't be bound at this energy. So, okay, the sun does that because essentially gravity pulls everything together and heats everything up. In our case, we have to think of a much smaller thing. We cannot do that. We have to, and we need a building. We need something to recover this radiation and this heat. The way we do that, the way we think of doing it, is plasma. As you can think, you have positive particles and negative particles all mixed together, but not bound to each other. So it's very magnetic. So if you put a very, very strong magnetic field, you can contain this plasma without it touching the walls. Because if it touched the walls, it would melt the walls and we would be lost. So that's essentially the big problem, is containing this plasma. Okay, this has been done one way or the other for the last 40 years, right? Lower temperatures than those, but we can do that. The second part is we have to know how will we recover this heat, right? The idea is to recover the heat from the neutrons, and there are several ways of doing that. It's under development, right? So there's a lot of effort going into this, but any deadline we give here is, as of today, just some piece of fiction, right? These predictions, they changed last year. There's this big, because some people say the clue to having it feeding itself and working all of the time with no problem would be to have a large enough system. Lab systems, they have problems in scale. They have too much surface to very little to low volume, and that's not so good. So they think, okay, if we build a large one, it will be what we call, it will produce more energy than it consumes, because it consumes energy to keep this plasma hot. It consumes energy to feed these magnets and everything. Right, so the first really big one that should have positive energy balance is this ITER that is being built in France, in Cadarache in France. It's an international conglomerate, just like CERN or something, independent to CERN, right? But it's the same concept. It should produce positive energy, not for power production yet, but just to prove the concept and to test, because there's several small things here that we cannot only test once we have a working prototype. And they had this prediction of going online in 235. They updated everything last year, but still keep the 2035 prediction. And they had the prediction that it would go commercial. The first commercial systems should be starting to go online at 2050. I think it will be later than that. Okay, but here's essentially what they're doing. They started building it in 2008, and they went until 2005 without major delays, and then things started to get delayed because of the pandemic, because of several other things on the way. Every time because no one has ever built something of this type, and you always encounter something that was not in your plans. That's part of being on the front of the technological. You're really on the edge of the technological knowledgement. Just a quick story. You may have heard that when they were upgrading CERN for the LHC, first time they tried to put the LHC, which is in fact a big tunnel, many kilometers long. It has to be under very strong vacuum, and the first time they tried to turn it on, almost all vacuum pumps blew at the same time. Okay, it's a great failure. Yes, but there's an explanation. No one had ever tried to do such a large vacuum system, such a large, high quality vacuum system. It was, 1,000 times larger than the best they had so far. So, of course, we will hit trouble. It took 1 year. They rebuilt it, redid the numbers, and okay, it's working fine since. So yes, there are delays, but we hope until 2035 we can have, the guys that work at this, they are sure 2035 is a feasible deadline. Let's see. And that's it for energy. Now, just for you to know, these classes are intended to be very short about applications, and each class will focus on different types of applications, right? So, bye for now.